Hello everyone, my name is Junzhi Wang. I'm a PhD student from Carnegie Mellon University. Today I'd like to present our work on a scalable and privacy-aware IoT service for live video analytics. This is a joint work with Brandon Amos, Anupam Das, Norman Sadi, and Mahadev Satya from Carnegie Mellon University, and Babu Pillai from Intel Labs. Video cameras are ubiquitous today. Surveillance cameras are widely deployed in buildings and public spaces. A survey in UK estimates there's surveillance cameras per 11 people. Lightweight portable cameras, for example GoPros, are highly popular among adventurers and travelers. Head-mounted smart wearables, for example Google Glass, are starting to emerge, and they often have cameras built in as well. Offering live videos from these cameras as a service offers high value. The rich information these cameras collect enables third parties to develop image and video processing algorithms to extract valuable information for the users. For example, we could detect liquid spills in shopping centers, identify a lost child before it's too late, detect IC patches on the side road. A business can determine whether their checkout line is too long and more cashiers are needed, or evaluate their window display by analyzing how long people linger before them. However, we're still far from the reality that we all can benefit from such analytics. We think there are two major problems. First, there's not enough bandwidth to stream all the videos into the cloud. Second, users have legitimate privacy concerns about information collected by the camera and what information can be extracted from these video streams. In this project, we aim to tackle both problems. To solve the bandwidth problem, we use the nascent model of edge computing that push the computation to the edge of the internet. Only extracted output of the analytics will be sent into the cloud. By doing so, we're able to support much more cameras and achieve a scalable solution. To address users' privacy concerns, we develop proof-of-concept systems that remove sensitive information from video streams. Now let's go into details of our solution. We use edge computing. Edge computing assumes small multi-tenant data centers, often referred as cloudlets, close to IoT devices. Instead of streaming input video stream into the cloud, they go into cloudlet. Privacy mediator virtual machines are running on the cloudlet that sanitize the video streams and remove sensitive information from them. They also publish these privacy-safe videos into analytics running on the cloudlet as well. Depending on different applications, they may choose to stream extracted information into the cloud. The benefit of using privacy media architectures are twofold. First, it provides a separation of trust. The entity running privacy mediator virtual machines is different from who is running analytics. It also improves scalability, because right now the information sent into the cloud are extracted informations. They are much less than raw video streams. The second part of our solutions address users' privacy concerns. We use the term denaturing to refer to the process of making a video safe from a privacy viewpoint. It's a trade-off between privacy and utility. The more information you remove from a video stream, protect more privacy, but the analytics can extract less information from them. Different denaturing mechanism offers different level of protection and user privacy policies to users. For example, if we use face detection as an underlying denaturing mechanism, all the faces in a video stream will be blurred. However, it is often desirable to selectively blur or show a person's face based on identity. Let's take the example of this picture. For the parents of the child on the left, it is often desirable for them to be able to see their children's face in order to track the child and also see the emotion of the child. So in our work, we focus on using face recognition as the underlying denaturing mechanism to achieve privacy, to help protect users' privacy. Our system design goal include we want our proof of concept to be highly accurate, run in real time, 30 frames per second, and also at the original resolutions of the video. The basis for our strong proof of concept is a highly accurate face recognizer. State-of-the-art face recognizers are deep neural network based. They are often trained with millions of proprietary data. Unable to acquire such data, we're forced to develop our own solution. So we built OpenFace. It is a DNN-based solution inspired by FaceNet. We trained it with 500,000 images we find from the public dataset. We use a combined approach of deep neural network and support vector machines. For each image, we first run well-known face detection algorithms on it to identify all the locations of faces. Then for each face, after some pre-processing, is fed into a deep neural network. The output of the deep neural network is 128 feature vectors. We use such feature vectors for classification. The benefit of such combined approach is we only need to train the deep neural network once and offline. To register a new face in our system, we don't need to retrain the deep neural network. We only use the deep neural network to extract the feature vectors and retrain the support vector machine for classification. By doing so, our training time for registering a new face will be on the orders of milliseconds a second instead of hours and days. To give you a sense on how accurate our detector recognizer is, here shows its evaluation on standard computer vision benchmark. The task is to predict whether pairs of images belong to the same person. Over here shows the ROC curve. A random guess for this task would result in a diagonal line. The area under curve would be 0.5. The ideal ROC would be a step function. The blue curve shows human accuracy. The green curve shows state-of-the-art commercial system that achieves human accuracy. Here is our OpenFace solution. We come close to the commercial system. If you use the popular face recognizer OpenBR before, this is their accuracy. And last, if you use OpenCV, the eigenface included in it results in such accuracy. Having a highly accurate face recognizers is only a basis for what we try to achieve. If we use a naive pipeline of running detection and recognition on every frame, we cannot achieve the real-time 30 frames per second that we want. On each frame, the face detection would take more than 100 milliseconds for an image of 1280 by 720. For each face detected, we need to spend another 30 milliseconds to run face recognition on it to identify who that face is. The result of a naive pipeline is we can only achieve less than 5 frames per second even when there's only one face in the image. To achieve our design goal of real-time and running at original resolutions, we leveraged object tracking, a cheap operation to perform to design an optimized pipeline. Here is how it works. When there's a video frame comes in, it is first feed into a dispatcher. Let's say the dispatcher determines it should go into a tracker. For the sake of this explanation, let's assume the tracker already knows the face on the right, and the face on the left just appeared. So in this case, the tracker would continue to track the face on the right, but the face on the left would become a privacy leak if we release this image immediately. But our system placed that image into a frame revisit buffer temporarily. Now here comes another image. The dispatcher determines it should be going through detection and recognition. The detection would detect the bounding boxes of faces in the image. The recognition would give out the identities of those faces and update the tracker. Now the tracker realizes, oh, there's a new face appeared in the image. And because of the temporal locality of videos, it's likely that we missed the face in a few previous frames. So at this time, the tracker would actually revalidate the images in the frame revisit buffer by backtracking the faces from the current frame. After revalidation is done, the previous image will be annotated with the two faces. Here comes another image. Right now, the tracker knows there are two faces and will be tracking them. The fourth image comes in. The frame revisit buffer becomes full, the oldest image will be pushed out. And based on users' denaturing policies, then will be denature the faces. Let's continue our example and assume we're taking the point of view of the parents of the left child. They want to see their child, so that they set their denaturing policies to show that child face. So the result would be their own child face shown and other children's blurred. By leverage tracking, we're able to achieve real-time and supporting 2 video streams on a 4-core machine. Compared to our baseline, the naive design, we consistently achieve a speed an order of magnitude faster. So in this talk, I've talked about some highlights of our solutions. There are a few more components and much more details in our paper. I haven't talked about the network structures of our face recognizer. We also deployed multiple optimizations to our pipeline in order to reduce privacy leaks. We also provide a mechanism for controlled reversal of denaturing when it's needed, for example, at the case of a court subpoena. We also have a detailed prototype design and implementations for an enterprise-scale deployment, covering how users would convey privacy policies to the system, and also how we can reduce the candidate pool that our face recognizers need to recognize from. We also talked about design choices for cloudlets in terms of different networking conditions and hardware configurations. That's all I have for today. Here is a demo video showing
RT-Face is a real-time face denaturing system that protects users' privacy.
Questions if there are.
It denatures faces in real time using object tracking